Single-ended and differential operation. A single-ended signal is defined as one that is measured with respect to a fixed potential, usually the ground. A differential signal is defined as one that is measured between two nodes that have equal and opposite signal excursions around a fixed potential. In the strict sense, the two nodes must also exhibit equal impedances to that potential. Figure illustrates the two types of signals conceptually. The center potential in differential signaling is called the common mode CM level. Here you can see the figure A single-ended and B differential signals. An important advantage of differential operation over single-ended signaling is higher immunity to environmental noise. Consider the example depicted in figure, where two adjacent lines in a circuit carry a small sensitive signal and a large clock waveform. Due to capacitive coupling between the lines, the transitions on line 2 corrupt the signal on line transition on line L2 corrupt the signal on line L1. Now suppose, as shown in figure B, the sensitive signal is distributed as two equal and opposite phases. If the clock line is placed midway between the two, and the transition disturbs the differential phases by equal amounts, leaving the difference intact. Since the common mode level of the two phases is distributed but the differential output is not corrupted, we say this arrangement rejects the common mode noise. Here you can see the figure A, corruption of a signal due to coupling, B, reduction of coupling by differential operation. Another example of common mode rejection occurs with noisy supply voltages. In figure A, if VDD varies by delta V, then Vout changes by approximately the same amount. That is, the output is quite susceptible to noise on VDD. Now consider the circuit in figure B. Here, if the circuit is symmetric, noise on VDD affects Vx and Vy, but not Vx minus Vy is equals to Vout. Thus, the circuit of figure B is much more robust to supply noise. Here you can see the figure effect of supply noise on a single-ended circuit, B, a differential circuit. Thus far, we have seen the importance of employing differential paths for sensitive signals. It is also beneficial to employ differential distribution for noisy lines. For example, suppose the clock signal of figure is distributed in differential form on two lines figure, then with perfect symmetry, the components coupled from Ck and Ck bar to the signal line cancel each other. Here you can see the figure reduction of coupled noise by differential operation. Another useful property of differential signaling is the noise in maximum achievable voltage swings. In the circuit of figure, for example, the maximum output swing at X or Y is equal to VDD minus VGS minus VTH. Whereas for Vx minus Vy, the peak-to-peak swing is equal to 2 into VDD minus VGS minus VTH. Other advantages of differential circuits over single-ended counterparts include simpler biasing and higher linearity. While it may seem that differential circuits occupy twice as much area as single-ended alternatives, in practice it is a minor drawback. Also, suppression of nonlinear effects by differential operation often results in a smaller area than that of a brute force single-ended design. differential operation by far outweighed the possible increase in the area. Thank you.